Hi there, welcome to the channel. If you're new here, this is a science slash bookish channel. So if you're curious about any of the two things, even though these days I've been mainly posting science content, stay tuned because I do have plans for bookish content, hopefully sooner than later, but they are to come. So again, stick with this video for a little bit. If you like it, hit the like button, subscribe, and leave a comment down below. It greatly helps for this content to reach more people that, like you, are interested in these types of things. Now, in this video, I wanted to take the time to talk about a topic in cosmology that is increasingly, you could say, fascinating me, slowly but surely. And that is the topic of dark energy. And dark energy is a very interesting, mysterious, you could say, thing to talk about when it comes to cosmology. And I have my reasonings as to why I think it is even more interesting and mysterious than some other hot topics in cosmology. But before we get into that, the main reason why I actually was quite curious to talk about this is because of all the recent buzz that has been going around on this result from the DESI instrument, where collaborators that use data from this instrument noticed that potentially dark energy may have an equation of state that is Elastus minus 1. And if you're in cosmology, this is a very damn big deal. But with a very important caveat that this was seen at least to be the case when not just looking at the result from the DESI instrument, but that combined with other observations, which is a standard thing that observational cosmologists do, like to look at any, you could say, observables, you could say, in cosmology, especially things like early universe cosmology or even late large-scale structure cosmology. They usually combine different surveys to try to find a nice overlap of all of them to agree on what they actually say. So in the case of this result that possibly shows that the equation of states for the cosmological constant may be different than what we thought, it is from a combination of surveys, and not just that, it is with a statistics or a variance of about 2.8 lower bound sigma and an upper bound, you could say, variance of about, I think, 4.2 sigma. So it is interesting, especially on that upper bound end, that we're getting to the 4 sigma mark, which is already always quite interesting for physicists, because it means if you push it a little bit further, you can get to the 5 sigma mark, which is really bona fide, almost undeniably. Something is definitely up and interesting. But for now, it is just, you could say, that is a peculiarity that we need to keep an eye on, but still something that can be ruled out by systematics, better data analysis, and what have you. And I have heard from other channels of people that are actual like experts in this field that there are caveats to these results and stuff. So do take it still with a grain of salt. But it still got me to think about what if, you could say, and what this would theoretically imply if this was a genuine result. And this leads me to why I like dark energy actually so much, especially now I'm slowly getting more and more curious about it. And that is because, in contrast to the main other mysterious thing that I know there is in cosmology that people care about, dark matter, I think dark energy is a little bit underrated. Even though I know professionally there are a lot of people that are working and interested in it, I think there's a lot more happening from what I've seen phenomenologically, even observationally, on dark matter than there is on dark energy, because dark matter seems to have a very broad, what I like to call theory space, like the space or the many, you could say, options of possible explanations for dark matter are very amplified. Like you have axions, you have WIMPs, you have many other interesting nuanced proposals, maybe things like sterile neutrinos and stuff, that can make you design experiments and observations that might set upper and lower bounds, although I think the lower bound is a bit more difficult, but you can definitely set upper bounds as to what dark matter may actually be. Because of that, I think it is a little bit boring for me personally, but I know many of my friends and people who are curious about it. But with dark energy, on the other hand, your observations that you can make to kind of infer what dark energy is very loose. And that makes it really intriguing to me. Because even before the late 90s, when observations were done with supernovae and noticed that, oh, you could say the Hubble rate which we're measuring seems to better fit when we include a cosmological constant that is positive and small, Even before that happened in the late 90s, there was very interesting things that were claimed about what if we do have a cosmological constant. For context though, for many years after Einstein came up with his field equations, which originally had this cosmological constant, but he included that in there to make sure that the universe was static, people did not bat too much of an eye anymore on what this cosmological constant may be. And as a matter of fact, Einstein himself famously removed that constant from his field equations. But from what I'm aware, this did not stop people from thinking about it still, because even if we were to assume that we live in a relatively globally flat universe, it is still quite mysterious that why we live in a precisely flat universe. It is one of those things that you might choose to care about it or you might choose not to. I think neither way it affects your day-to-day life, even as a theoretical physicist. It is one of those things that is, you could say, almost a bit of a philosophical question. You can take it that far. But there are more concrete reasons also as to why people were thinking about the cosmological constant in more serious ways. And one of them came from the fact that if we were to assume that a cosmological constant were to be out there, even without calling it dark energy or anything, if we were to assume that that's a thing, there has been attempts already in the past to calculate, you could say, the vacuum energy of, you could say, just space-time. This has been done by Pauli, I think, in the late 20s, and also by others, and it has led to people finding a relatively large number for it, actually. And the reason why I'm actually quite excited to talk about this and wanted to even make a video is because I actually read a paper, a very short one, quite thoroughly, that was written by Stephen Weinberg. I think it's called Anthropic Bound for the Cosmological Constant, and it was published in the late 80s. And this paper is quite interesting because Weinberg tried to, well, as you heard it in the title, use anthropic reasoning, which of course is a very controversial thing to do because it almost feels like a cop-out when trying to explain something. Like, anthropic reasoning, for those that don't know, is this type of reasoning that you do where you try to make sense of something, whatever it is that you observe, by stating that, oh, the reason it is so, even if I can't really explain it otherwise, is just because it is suitable for especially life. So, for example, you can use this not just in physics, but in chemistry as well. Like, if you were to use why is, for example, the fine structure constant the way it is, so why is the strength at which electromagnetic interactions happen the way it is, well, you can say that, okay, because we live in a universe where it is the way it is, because otherwise you wouldn't have had a lot of proper chemistry happening, because the strength of electromagnetic interaction really determines, for example, things like the radius of atoms, as well as how covalent bonds form and such, and of course, naturally, how organic chemistry, biochemistry, and eventually life happens. So people tend to use arguments like that, and this is something that Weinberg tried. He said that, oh, because we don't have a good reasoning, this is, by the way, stating verbatim from his paper, because we don't have a good reasoning for saying that the cosmological constant is exactly zero. And again, remember that this was at a time before the dark energy discovery was even made. So he was swimming in uncharted territories here. He said that, okay, because we don't know why lambda should be zero, let's try to use some sort of anthropic reasoning to do this. Let's say that we have a universe with zero curvature, so a flat universe. This is still an expanding universe, but it is not hyperbolically curved, nor positively, aka closed, curved. And in that universe, we set a subsystem in place. We set a small spherical density, you could say, clump. We don't even say exactly what it is, but we have a small density clump, say dust or something along those lines, that has a positive gravitational potential. That is super important. That positive gravitational potential means that structure can form. So you're assuming you have a substructure in that flat universe, which allows for large structure formation. And the reason this is some sort of anthropic reasoning is because you assume that in order for stars to form, in order for that to have this dust around it, such that planets can form and eventually life could form, you need, well, gravity to hold things together. So you need a gravitationally bound structure. So this is exactly what Weinberg did. And okay, so this is future me in Toronto interrupting the flow of what you were seeing, because I noticed the first time I recorded this, I was a bit wrong. And in essence, what you have is that you set up the Friedman equation, not for the universe in it of itself expanding, but you set it up to look at this subsystem within the universe. So in this sense, the scale factor, for example, and the Hubble rate that describes the change of the scale factor with respect to time is looking at it in the sense of this small spherical subsystem, this gravitationally bound system, and how that is changing with radius over time, etc. So on the left-hand side, you have this, you could say Hubble rate, or this expansion rate for this object, this scale factor for this gravitationally bound system. And you also have on that same side this delta K, which just tells you about the curvature content of this object. Because it has a positive gravitational potential, it has some sort of curvature. And on the right hand side, you have your standard, you could say, constants, along with different densities, which tell you one, just a simple rho, which tells you the overall density that is in the surrounding system, which is the universe. You have a delta rho, which is, you could say, the overall perturbation in density that you get from this subsystem. And you have this rho lambda, which is going to be this factor of the overall rho that comes from this vacuum energy, whatever it may be. And in essence, you get that when sending the delta K term over to the right-hand side, you're left with, you could say, an expression that tells you something about the Hubble rate, or the rate of change for the scale factor with respect to time for this subsystem. And if you want this system to be gravitationally bound, you want its, in essence, its scale factor, or its radius, for lack of a better word, to start decreasing, because gravity clumps things together. And in order for that to happen, that means that the dA dt needs to be decreasing, so it needs to be smaller than 0. And to have it to be smaller than 0, you need to have this inequality, which you see right here. What you end up with is that the density parameter for this vacuum energy, which was in the density parameter stuff to begin with, that must somehow be smaller or equal to something like 500 times the original density parameter of our universe today. So in essence, there's an upper bound, and a quite large one at that, as to what value this vacuum energy could have for large-scale structures to form. So with this liberty of this vacuum energy to exist and be actually quite high values at that if it exists, why is it that the observed value of it is quite small? And again, this was before the 90s, so before we had really precise measurement of this density parameter for vacuum energy. But Weinberg himself did a really clever, quick, and dirty calculation where he said that, okay, if at the time what they had access to were these quasar measurements, which are the supermassive black holes in the center of galaxies that emit really bright jets, so they're really active, you could say, they allow you to very accurately measure distances, you could say, over large patches of space. So by measuring distances to these quasars, you can accurately tell what structures you have at what specific distances. And astronomers often use the term redshift to denote this. And redshift can tell you something not just about distances, because of how light is being stretched over those distances, but it can also tell you something about time. Like the higher the redshift you look, the further you're looking back in time. So what Weinberg did is, with, you could say, quasar information, he extrapolated that, okay, so if the universe was a certain age at this particular redshift, which I'm dealing with, then that means that large-scale structures could already form by a certain amount of time. And with that, he can kind of infer what that means for, you could say, the bound, the upper bound for this vacuum energy, given a universe that exists with some matter content already that allows for the gravitational collapse at such, you could say, earlier times. What this turned out to be is that the value for this density parameter of the vacuum energy was already quite significantly smaller than what you would get with his anthropic bound. So the question then became, okay, so if this observed cosmological constant, if there is a cosmological constant to begin with, does exist, then why is it so much smaller than this anthropic bond that I said? So in essence, this anthropic bond perhaps might not be enough to say why the cosmological constant might be small, if it exists to begin with. Now, then you enter the late 90s and people did their measurement with supernovae, and we did find out that there was a cosmological constant. And again, strike contrast to what has been done with the quantum field theoretic approach, this cosmological constant was indeed quite small. And this led to the content of many observational lists because it could explain certain things about the age of the universe that they were puzzled by, but it brought pure havoc to theorists because theorists could not exactly figure out why this thing is so small as it was, especially in contrast to the QFT calculation. There are today various proposals as to this, and again, with the recent DESI result, it makes it even more interesting if they are able to do their analysis and find out indeed that the significance of what they found might indeed be somewhat true. And for example, this could include models of dynamical dark energy. There have been models since the 90s where people impose that the dark energy is something like another field, a scalar field. This is often called quintessence, that is evolving dynamically, aka it has a magnitude that is time dependent. So over time, this field can weaken or get stronger, but most of the time it gets weaker as the universe expands, and that could explain why the cosmological constant might not be constant. That at maybe in the very early universe it might have been quite strong, and today when we observe it, it is quite weak, and it maybe just gets weaker. But there are also other proposals. For example, one of the most, you could say, edgy ones out there is something called timescape cosmology. It is edgy, but in reality, I'd say it's quite conservative. And what it says is, in essence, that there is no cosmological constant. That what we observe with, you could say, this perceived or a perceived accelerated expansion of the universe might be purely because of inhomogeneities of the universe. If inhomogeneities were large enough, so say if we have a lot of void structures in the universe, which we do know that there are a lot of void structures out there, then that might mean that because of these void structures, there is a different gravitational potential all around the universe. And if you have different gravitational potentials, you also have different passages of time because time or the flow of time is affected by gravity, by gravitational potentials. So in essence, this model is proposing that maybe what we observe as some patch of the universe expanding maybe faster and faster away from us might just be the result of cosmological time dilation, which is at least I must admit to me, quite interesting and quite conceptually appealing because it explains this phenomena in a way that doesn't include, you could say, very exotic new physics and new degrees of freedom. But the only thing is that matching this with precise precision measurements of cosmology, like, again, baryonic acoustic oscillation measurements, or especially acoustic peaks from the cosmic microwave background, it's extremely hard without some extra, you could say, modifications and parameter fitting of timescape cosmology, which makes it not as attractive, yet at least. So that kind of kills many arguments for timescape cosmology, at least up till this moment, and at least up till what we have right now with this DESI result. Maybe, again, observations that are coming up, like from the Euclid satellite, might also be quite interesting for narrowing down the equation of state for dark energy, since it is one of the main tasks that are going to happen with these large sky survey sweeps. But there is another paper actually that I'm quite interested in. I haven't read and broken it down as much as I had the Weinberg paper. And this is a paper I think called The De Sitter Spacetime and the Swampland. This was written by Kumrum Vafa and collaborators. And this paper is quite interesting, not only because it is very heavily cited despite being very recent, like from 2017 or so, but also because it proposes something quite daring from the base that I saw. And that is, in essence, that string theory, under good assumptions or under the assumptions made from some of the swampland conjectures, omits a de Sitter universe, which is quite daring. It is saying, in essence, that there shouldn't be a de Sitter universe to begin with, according to string theory. And the reason why that is a bit of a very strong, bold statement, let's say, is because the universe as we observe it today is pretty much de Sitter. It has a positive cosmological constant that we measure. So, what does that mean in essence if we don't have a de Sitter space-time? The paper flashes this out and talks about the various implications of that, but in essence, I think it uses things like certain no-code theorems that kind of really state what is allowed in terms of cosmological evolutions and what isn't, and as well as tying those to like problems of string theory. So I think that is quite interesting that there is something there. I haven't read this paper again thoroughly because I don't think I have enough background, especially in string theory, to talk a little bit more strongly about this. But I do think it's interesting because, for example, the reason this is interesting though is because I know very loosely and conceptually though, like in the very popular sciencey way almost, that in string theory, when if you wanted to work, especially if you wanted to be like perturbatively well behaving, you would have many, you could say, possible compactification of the extra dimensions which you need for string theory to actually work and be renormalizable and be perturbative. And I think it is something about 10 to the 500 or so vacua. And the swampland program, in essence, is a program that tries to set in as many well-motivated, you could say, conjectures as possible to rule out, you could say, vacua possibilities that may not be our actual universe and leave in only those that may describe our actual universe, physics, gauge theories, and everything that comes with that. And even then, by pure probability, there might be more than one vacua that may fit the laws of physics as we know them to be, or very close at least. And I think from what I've heard is that string theorists used some sort of anthropic principle to state that, perhaps there may be more than one universe that allows the laws of physics to evolve in very similar ways. So it kind of explains a sort of multiverse scenario where you kind of say that some of these other, you could say, vacua for string theory kind of leads to other universes. And you can kind of tie that very hand-wavily to other inflationary models, like if you care about cosmic inflation, such as chaotic inflation by Linde, where instead of inflation happening just once, so you're having this rapid exponential expansion of the universe, you may have inflation happening, and when you look at the potential of how this goes, it might go very steep. So in essence, the inflationary field kind of loses energy very slowly, and in that process you can have different patches of the universe kind of leading to its own inflationary moment if this decreasing of the magnitude of the inflationary field happens slow enough. And this is kind of the idea behind chaotic inflation, that inflation can kind of happen eternally almost. And this could lead to a multiverse scenario that might be linked to what string theorists want to use their anthropic reasoning for. Again, very much on shaky waters, if you ask me, but mainly because I don't know much about this stuff. But I do find it interesting, and I wonder if you find it interesting as well. I'm curious to read a little bit more about this because it seems to especially become likely a bit more relevant, and we're likely going to see a lot more papers as DESI continues to improve on its measurements and analyses, as well as when we especially get like something from Euclid. So it seems like it's going to be exciting times, especially regarding to questions about dark energy. And I'm curious if any of you have also thought about this, and if you have anything to say, I'd love to hear it in the comments down below. Thank you for sticking in with my rambling thoughts, and I hope to see you sometime soon again. Bye-bye.